All right, so before we can start talking about rotational spectroscopy, we got to talk about rotational energy levels, right? Because again, for any type of spectroscopy, right, what we're concerned about is what is the change in energy between some initial to final state, right? Because that change in energy is going to be equal to the energy of the photon that is absorbed or emitted, right? Which is related with h nu, for example, right? And so we need to talk about what the energy levels are for three-dimensional rotors, okay, rigid rotors here, and relate that to what we talked about with three-dimensional rotations before and energy levels there. Right? So in a previous video, we talked about different types of rotors, right? We talked about symmetric, asymmetric, linear, and spherically symmetric rotors, okay? So here we'll start talking about symmetric rotors. So for a symmetric rotor, okay, I have a case where, again, two of the moments of inertia are equal and one is not, and that one that is not also equal to 0, okay? And so the energy for that rotational object, right, is given here, JA squared over 2IA, JB squared over 2IB, so on and so forth, right? J here, okay, is referred to as the total angular momentum, okay? We've often used L for angular momentum so far, and L is related to orbital angular momentum. So L often is used to indicate, right, this is orbital angular momentum, okay? While J is referred to as angular momentum of rotation of a molecule, okay? So J's general type of angular momentum description, and it's used often when talking about molecular rotations, right, and not orbital angular momentum, okay? And so the J's here, right, this J value, say JA, right, is your angular momentum in the A direction, right? This is just your angular, right, momentum in a direction, right? So angular momentum in the A direction, JB is angular momentum in the B direction, right? This is the same type of thing as a linear momentum, right? Where for linear momentum, I would write this as px squared over 2m, right, plus px or py squared over 2m plus pz squared over 2m. Now the mass is the same as you're moving in x, y, and z directions and things like that. So, right, so this, right, thing here for translational energy, this is for translational, right, kinetic energy, that is, right, going to have the same mass in every direction, right? But here, for rotational, these moment of inertia depend on what direction you're rotating, and so they will potentially be different, right? So now, using the fact that we're talking about a symmetric rotor, right, I can simplify this expression to this guy here, right, as the expression for the energy of a symmetric rotor that's rotating in space based off of its angular momentum in the A, B, and C directions, okay? Right, so I'm going to use the fact, right, that my total angular momentum is just the sum, right, J squared is sum of JA squared plus JB squared just plus JC squared, right? It's the same thing as, say, your momentum squared, again, is the same as px squared plus py squared plus pz squared, okay? So the same type of principle, right, in linear momenta applied as to angular momentum, right? And so I'm going to use that fact, okay? And what we're going to use here is I'm going to add and subtract JC to this first term, okay? So that I can simplify this as J squared minus JC squared, okay? Which then leaves me with this term here, right? Where I have my energy in terms of the total angular momentum squared, right? Divided by 2 times the moment of inertia in the B direction, right? Plus the difference in 1 over these moment of inertia times the angular momentum in the C direction. So we do that, we want to define our total angular momentum expression, right, here, because we know in quantum mechanics what J squared is, right? J squared, the total angular momentum, is related with the quantum number J times J plus 1 times H bar squared, right? This is the same thing as saying L squared equals L times L plus 1 H bar squared, okay? So in terms of my J quantum number, okay, I know my total angular momentum is just J times J plus 1 times H bar squared, okay? Now, in terms of what JC is, right? So C is some arbitrary direction, okay? And so I can pick that direction to be whatever I want. I'm going to call that C direction, that C axis, my Z axis, okay? And so just like how M sub L was the rotation, was the orbital angular momentum along the Z axis, right? That M sub L is going to be the same type of thing as J sub C, right? And so, therefore, J sub C is going to be related to this quantum number that we're going to call K times H bar, right? Right, let me rewrite this, because really it should be, I should be saying, right, that the orbital angular momentum in the Z direction equals M sub L times H bar. And so similarly, we're going to say the orbital angular momentum, the rotational angular momentum in the C direction for my molecule is related to K times H bar. So M sub L and K are the same type of quantum numbers, and L and J are the same type of quantum numbers. So they obey the same set of rules. L and J, right? L, right, goes from 0, 1, 2, 3, so on and so forth, right? J does the same thing. J 0, 1, 2, 3, so on and so forth, right? M sub L goes from negative L up to 0, all the way up to positive L, right? K goes from negative J, right, to 0 up to positive J, okay? And so, like, the J and K quantum numbers are the same type of things as L and M sub L. We're just giving them different labels, okay? Because we're referring to total angular momentum of an object rotating in space versus orbital angular momentum of an electron orbiting in a nucleus, okay? Right, and so plugging that information in, we get that the rotational energy level for a symmetric rotor, right, so this is for a symmetric rotor, right, so for a symmetric rotor, right, I get that the total energy is equal to J times J plus 1 times H bar squared over 2B plus 1 over the difference of these moments of inertia in the B and C direction times K squared H bar squared. Okay, so that is my energy levels for a symmetric rotor. Well, now, before we go on to talking about linear rotors and spherically symmetric rotors, I want to just talk about the fact that often in rotational spectra, we're going to define a quantity here, this rotational constant, which is going to be defined as such, okay? So HC times B is equal to H bar squared over 2IB, okay? Or B itself is given by this equation here. And the reason we'll do this is B here has units of inverse centimeters, okay? So the reason we define B as this, as units of inverse centimeters, okay, is because of the fact that often when we talk about the energy of our light, we can write the energy of light as energy equals h nu, right? But I can also write this as hc nu bar. This nu bar is often referred to as wave number, right? This is your inverse centimeter unit, okay? Nu bar is equal to 1 over the wavelength of that light, okay? And so we do this because what we'll see later on when we talk about rotational spectra and such is that if we define this rotational constant B, okay, as such, then what we'll be able to do is when we look at rotational spectra, we'll be able to read off from that spectra the value of B very simply and very easily, and then we can use the value of B and then this relationship if we want to calculate, say, the moment of inertia of my molecule. Okay, and so this rotational constant is used to just kind of simplify things down and then make interpreting spectra simpler. Okay, so using that definition of B, right, and that definition of, say, B was just in terms of IB, I can define this C tilde in terms of IC, okay, and using that definition, I then get this simplified expression for the energy of my symmetric rotor, okay, so HCB tilde times J plus 1 plus HC times C tilde minus B tilde times K squared, okay, right? And so we'll kind of note just briefly about some degeneracies and things like that. When K is equal to 0, right, you have no angular momentum around that C axis, okay, and those energy levels, right, is singly degenerate. But when K is non-zero, then you have some angular momentum around the C axis, okay, and you'll have the doubly degenerate energy levels, okay, because, right, K squared is the same whether or not K is greater than 0 or less than 0, right? Right, that gives you the same number if it's less than 0 or greater than 0, so if K is equal to minus J, that gives me the same energy as when K is equal to J as well. So these would be doubly degenerate, okay, energy levels for symmetric rotor, okay. So when K equals 0, I have single degeneracy, right? There's no degeneracy, basically non-degenerate. When K does not equal 0, I'm doubly degenerate, okay? All right, so now talking about a spherical rotor. Spherical rotor is a little bit simpler, okay? All of these moments of inertia are equal to each other, I, B, and C. Okay, so following kind of the same steps as we did for symmetric rotor, okay, what we see is for a spherical rotor, right, the total energy is just going to be related to this equation here. EJ is J times J plus 1 times, it should be H bar squared, okay, over 2IB, right? And then using the fact that defining B as such, H bar over 4 pi C IB, we get that when we plug that in, we get that the energy for a spherical rotor, spherically symmetric rotor, has this energy level, which does not depend on K whatsoever, okay? So it's independent of K, right, completely. So it'll end up having the same degeneracy as a, well, it'll have greater degeneracy, I should say, than a symmetric rotor, right? Because now, right, if J equals 2, right, K can equal minus 2, 2, minus 1, 1, and 0. And all 5 of those K values have the exact same energy, right? So the degeneracy here is going to be related to 2J plus 1. Okay, so that's your degeneracy for your rotational state, right, for a spherically symmetric rotor. Okay. And so kind of showing why we use these wave numbers, right, is if I want to look at the energy change between, say, the J plus 1 and J energy level here, right, I plug in J plus 1 into the energy for my spherically symmetric rotor. I plug in J, take those energy differences, and I'll see that this delta E, right, is related to 2HCB times J plus 1. Okay. And so again, if I write the energy of my light in terms of wave numbers, okay, which this 1 over lambda is equal to your wave number, which is nu tilde, okay, we see that the wave number, right, when simplifying is equal to 2b times j plus 1, okay. And so the whatever wave number your peaks occur at are directly related to this b constant as well as in the value of j, okay. Right, and so for a linear rotor, right, this we had done when we talked about orbital angular momentum, right? For orbital angular momentum, we considered essentially a linear rotor. We considered two objects that were, two masses separated from each other rotating in space. That is a linear rotor, right? And the energy we solved for that was just J times J plus 1 times h bar squared over 2I, okay? Okay, and so we'll note here that, right, the note here at the bottom is just talking about the fact that K always has to equal 0 for a linear rotor, and that's just because there is no angular momentum around, say, the spinning axis. Because we're going to, this is sort of an approximation, right, because technically there's an angular momentum because your atoms have some size to them, and so you're rotating a sphere, and that does have some type of angular momentum. Okay, but the size of your atoms are so small, right, that it really, the angular momentum of rotating around your axis like this, right, or if you're looking down the axis, right, rotating down this axis of the pen, right, is not really, like, the effective angular momentum that it will have is so small that it's, I'm not going to say it can't be measured, but it's small enough that we never care about it. Never going to really measure it unless you really, really want to try to, okay? And so K for that is always going to be as 0, okay? You're never going to rotate for a pure linear rotor, right? For an idealized linear rotor, K will be equal to 0. Now, again, in real life, we don't have an idealized linear rotor, right? There technically is some angular momentum around that one axis. It does not equal 0. The moment of inertia around that axis C, okay? But when the moment of inertia around that axis is equal to 0, okay, or essentially 0, then K itself will always then be 0. Okay, so here, just kind of summing up, right, what the energy levels are and then the degeneracies for these different energy levels, right, for spherically symmetric rotor, linear rotor, and symmetric rotor, okay? Right. So now I'm going to talk a little bit more about degeneracy and the fact that there is technically a rotation around, say, the laboratory axis, right? Your molecule is rotating freely in space, right? But that rotation, right, where does essentially like IA, right, the moment of inertia in the A direction, B direction, C direction, where are those directions pointed relative to your laboratory axis, okay? And so that laboratory axis, we're going to have the value of m sub j related to it. So we're going to assume, right, laboratory, right, is got this z direction here, and in that z direction is the angular momentum around that, right? So the angular momentum around the z direction is related to m sub j h bar, right? So it's your rotation around the z direction in the laboratory axis, okay? And assuming no external magnetic fields or other things like that, right, the rotation around that laboratory axis is completely arbitrary, okay, and it will not, right, depend on K or m sub j, your total energies, okay. So basically, the degeneracy of your states gets multiplied by 2j plus 1, right. So because of this laboratory axis, right, there's an extra 2j plus 1 degeneracy for each energy level, okay? So for a spherically symmetric rotor, that means you get 2j plus 1 times 2j plus 1, which is 2j plus 1 squared. For a linear rotor, okay, you just get 2j plus 1 because it has a degeneracy of 1 initially, but now it's 2j plus 1 since the energy does not depend on m sub j. And then for a symmetric rotor, you get 2 times 2j plus 1 when k does not equal 0, and then 2j plus 1 when k equals 0, okay? And this degeneracy is broken only when you apply an external magnetic field, right? Because once you apply an external magnetic field in your lab, there's now a difference between the x, y, and z axis in your lab, and so the degeneracy of rotation around this laboratory axis is broken, and this is referred to as the Stark effect, and we'll talk about that in future videos. Okay, and so that wraps up our kind of introduction of the energy levels for rotational states and their degeneracies. Okay, for rigid rotors. Notice here we did not talk about asymmetric rotors. We're not going to talk about them. Okay, so we'll only deal with these three classes of rotors: spherically symmetric, linear, and symmetric.